So Don was a good friend and a great physicist, and it really is, in that cliched phrase, a pleasure and honor to speak at this meeting about his contributions to our understanding of charge current neutrino interactions. Don wrote something like 100 papers, or was co-author of 100 papers on charge current neutrinos, covering many different things. But probably the majority of them were on deep inelastic scattering, where he made really seminal contributions, and that's what I'm going to discuss. Now, Don first became involved with neutrinos at a summer study at Berkeley in 1961, where we were looking at a possibility of building a 200 GeV machine, which ended up as a 400 GeV machine at Fermilab. And John was charged in looking at the characteristics of secondary beams, and he designed a narrow band neutrino beam, probably the first time anybody had even thought about such a thing. Now, at that time, there was a race between CERN and Brookhaven to test the two neutrino hypothesis. CERN was in pole position because the first beams circulated in the CERN PS 8 months before the first beams in the AGS of Brookhaven. But an experiment that was planned using an internal target was cancelled when it was realized that the neutrino facts had been overestimated by a certain Jack Steinberger, incidentally, by at least an order of magnitude. Now, Don, wait a moment, how did I do this? Don wrote later that Mel Schwartz told him that at Brookhaven, when they heard the CERN project had been dropped, they could hardly believe their luck, and 3 of them went on to win the Nobel Prize. Meanwhile, at CERN, a wideband neutrino beam had been built with Vandermeer's famous magnetic horn, the Swiss Strategic Steel Reserve as the screen, and 2 neutrino experiments. The first results were announced in conferences at Brookhaven and Siena. And behind the shielding, the first thing was a 1.2 meter bubble chamber full of freon, and originally later propane. And behind that, there was a spark chamber. And then about a month later, there was the big international conference in Siena. And there were 8 talks in a parallel session on the CERN neutrino experiment. And Don was the speaker on the results from the freon chamber. And I'm delighted that Gerald Myatt, who is one of the people you see on the author list here, is with us today. And I know that Don Cundy, I think, is looking, I hope is looking, said he would try to log in online. And he told me that he would alert any other survivors of that group of people who might like to see this talk. Now, I'm going to move sideways. First, the results of that experiment and the Siena conference. According to Don, it was chaotic. He said that Bernardini, who was the research director at CERN, wanted to have a rehearsal or a sort of dry run to compare what the 7 different CERN speakers would say, but he wanted to be in secret. And he convened a meeting on the roof of the Siena town hall after dark. And Don says it's completely amazing that nobody fell off. The main focus after the discovery of 2 neutrinos was on finding the W, which we thought, even when I was a student, might have mass like the Rho meson or something like that. At the end of the conference, in the plenary session, Luis Alvarez asked Bernardini, well, come on, tell us, give us a summary, have you found it or not? And Bernardini said that they've found dilepton, electron and muon events, which might or might not be due to production and decay of the W boson. These events were probably early examples of charm particle production. And they were not, there were other early hints of things found later. First of all, the results showed a marked increase of the inelastic cross-section with energy. now known to be suggestive of point-like behavior. Don went and spoke to Bell and Veltman about them, and Bell told him, being very hard to understand these multi-pion events, why don't you do something useful like testing PCAC or measuring elastic scattering or n-star production? The next year, there was a short anti-neutrino run, but the results were never published, except in a thesis by a certain Enoch Young. Enoch Young was a Chinese graduate student of Don's who went back to Hong Kong. He'll feature in my story later. They were never published because they didn't understand them. There were fewer charge current events than expected, and more events without muons than expected. And we now know this is because the cross-section for antineutrinos is much smaller than for neutrinos. But in those days, everybody knew that particle and antiparticle cross-sections were the same at high energy. And they didn't, and the events without muons were, of course, neutral currents. It was not possible with that small chamber, and Dieter will explain why, to show that they were neutral currents. But just after neutral currents were discovered, Don reanalyzed the early events and found them that they were in excellent agreement with the Gargamelle results. Of course, with an infinite systematic error because you couldn't prove that they were neutral currents. Now, I'm going to move slightly sideways for a moment on deep inelastic scattering. In 1968, the first results of the classic SLAC-MIT experiments were announced at the Vienna conference. The scattering cross-sections were much larger than expected by almost everybody, and to first approximation, the dimensionless structure functions exhibited Bjorken scaling. The group knew well that this suggested from point-like objects, but voted that against his wishes, and he's told me this, Jerry Friedman, the speaker, should not say so. However, Panofsky, who was the rapporteur, didn't know about this vote. And speaking as rapporteur, he said theoretical speculations are focused on the possibility that these are evidence of point-like behavior, charge structures within the nucleon. The only person who probably wasn't surprised was Jim Bjorken. BJ had inferred in 1967 from a sum rule of his own and the Adler sum rule, which I'll come back to, that the cross-section for electron-positron annihilation to hadrons should vary as 1 over e squared, the deep inelastic should be point-like, and the total cross-section for neutrinos should rise linearly. He actually, at that point, had the physical picture, which we now call the Parton model, though he didn't write it down explicitly. A couple of years later, he, quote, derived by formal methods, which we now know to be invalid, Bjorken scaling. His paper ends, a more physical interpretation of what is going on is without question needed. So curiously, BJ had partons without scaling, and then he had scaling without partons. But this is just indicative that we really, none of us knew what was going on at that time. Don wrote later, immediately I saw the SLAC data, I realized what an idiot I'd been. I dashed back to CERN and replotted the Freon and propane data, which was taken in an experiment in which Don was not involved in 1968, and saw that simple linear dependence of the total cross-section. They'd never plotted the total cross-section. They looked at elastic scattering, single pion production, and multi-pion production. They knew there were a lot of multi-pion events, but they never plotted the total cross-section. Now, Don showed what he discovered between September 68 and January 69 in the topical conference on weak interactions at CERN. And this is maybe the point to say something about my own relations with Don. Don arrived in Oxford in 1965. I was a second-year graduate student. I don't think I ever spoke to him then, but I saw him in the seminars organized by Dick Dalitz. Those took place, what we now call the Dennis Wilkinson building wasn't finished, across the road on the other side of the Banbury Road in the old high school. And they took place at 8 o'clock at night, and Dick would arrive with a breathless, rather bemused speaker who he'd just taken to dinner in All Souls. Don was there puffing his pipe and asking his usual excellent questions. At this conference, he showed that the Freon and proton data exhibit qualitatively much the same behavior as seen as SLAC, though the number of events was small, the precision much poorer, the incoming energy lower, and in fact not fixed. He then showed the Adler sum rule. That's the form in which it's shown today, but we didn't use that notation in those days, in this form of differential cross-sections. And he recalled that, as pointed out by BJ, it's highly suggestive of point-like behavior. Now, this sum rule was thought of as some sort of arcane thing from difficult calculations with commutators going to infinite momentum and so on. And there was no picture, it wasn't really connected with the Parton model, but he continued, there's another way of thinking about this, and that's to postulate that we're scattering from point-like particles. And then he described the Parton model, basically, and said that then the d sigma dq square will be a constant, and the constant factor could be interpreted as the constant difference between the number of constituents with isospin up and down. That's exactly the argument that BJ had used when he'd come up with the ideas. The model's unbelievably crude, but it has the value of making rather definite predictions. For example, that the neutrino-neutron and neutrino should be twice the neutrino-proton cross-section at high energies, provided a typical Don phrase, provided infinity is not too far away. Then, we didn't know this was the right picture, referred to other possible interpretations. I'm now going to move sideways for a couple of slides on theoretical developments that happened before Don appeared on the scene again. Oh, no, I haven't finished what he said in the conference yet. He showed the total cross-section, and here you see it rising linearly. The slope's actually slightly higher than that, but there's a huge error than the 0.6. But he remarked that the constituent model will also predict a linear dependence with a coefficient of 1.4. The coefficient's actually about 0.7, and that's because half the momentum of the proton is in gluons. And at that point, people were thinking the Quark model meant quarks, nothing else. God knows how they were held together, but nothing else. Now, as I said, I'm going to move sideways. In the beginning of 1969, Kurt Callan and David Gross, using formal manipulations, taking Q to the momentum transfer to I infinity, the momentum of the proton to infinity, manipulating things, related the structure function F2 to F1 to the commutator of the time derivative of a current and a current. Now, the time derivative of the current is a commutator of the Hamiltonian with the current, so it brings in dynamics. And they pointed out that it would be different in the Quark model than in an alternative model of current algebra, which was around at the time called the algebra of fields. We didn't know what sigma L over sigma T. This is the cross-section for longer scattering of virtual, longitudinal, and transverse photons, in the case of the SLAC data. We didn't know what the ratio was because the SLAC data, the first run was a relatively small angle and it's only sensitive to F2. But in the next year, they looked at wide angle and we were all agog. What's the answer going to be? And this was the result, 0.2 plus or minus 0.2, which was music to the ears of those of us who thought that quarks should be taken seriously. The next big milestone was what's the difference between neutrons and protons? And that we had to wait another year, but the structure functions are not the same as predicted by some of the models that were on the market. In the spring of that year, David Gross was visiting CERN and he gave a talk about all the different approaches to the deep inelastic scattering. I hadn't understood Don's talk or that part of it, but I knew something about neutrinos. And I applied the Parton model to neutrino scattering to see if I'd understood David's talk. And I went to his office and said, I've worked this out in the Parton model, did I get it right? And he looked at me and said, nobody's ever done that. That's a good idea. And then when he'd figured out that there was a third structure function, we derived a certain sum rule. But David said to me, the 2 was up on the right and we had 6. He said, we must have made a mistake. The sum rules give 1 or 2, they never give 6. And then that evening I figured out that we'd found a way of measuring the baryon number, the difference of the number of fermions and antifermions in the nucleon. I'm going into this because Don did a lot of testing these things later, and also the things on the next slide. And I forgot to say, oh yes, I did say how I'd met Don. Now, in 1970, there were a huge number of ideas still around. They weren't sorted out. But I thought it'd be interesting to derive all results that are true in the Parton model with very formal manipulations, even if there are interactions and so on. The most interesting are the second one there, relating the electron scattering to neutrino scattering. That's an equality if there are no strange anti-strange quarks in the nucleon. It looks like a good measurement of quark charges. On the other hand, it was known to be right. It just says the isoscalar over isovector current scattering is 1/9, which was known to be true in electroproduction. Maybe it had nothing to do with quark charges. I also showed that, in a model with 3 quarks, the integral of F2 for electrons would be 1/3, and the data said 0.18. And it was bigger than 2/9, even if you had a quark anti-quark C that swamped everything else. But I said it's easily reduced by adding a background of neutral constituents which could be responsible for binding quarks. This was attacked as not in the spirit of the quark model. And the next year I had a sum rule for the momentum. Using the Perkins analysis, which I'm coming to in a moment, this gave a value of 0.52 with a big error. The first time I met Murray Gargamelle, after telling me that I spelt my name wrongly, he told me that he knew my paper, very pleased about that, but we should ignore this. We should continue to think about just taking algebra out of free quarks, didn't take quarks seriously. Now here's the Perkins paper. The results, the analysis that Don showed in the conference at CERN were published by Burdigoff et al. In October 69, and this was followed in March 71 by a more detailed analysis by Gerald here and Don. It showed evidence for scaling, Q squared increasing with the energy. They showed that the data could be used to figure out that the neutron cross-section over the proton cross-section was 1.5, and the simple quark model would be 2. And then they looked at the different structure functions. That line on the right is the spin-a-half model, and the data are somewhere. Does this pointer work? Never mind. Down near the bottom. This was a really important paper. It was manna from heaven for those of us thinking about these things, because it's the only thing we had to go on to think about what we were going to see next. And in the physics report that I wrote, which was the only big reference on neutrinos in those days, I devoted 4 of 110 pages to that paper, though I was a little bit worried that the energy was too low for it to be asymptotic. Now, by 1972, though, I won't spend longer on that paper because the situation was transformed when the first results came from Gargamelle. And in the international conference at Fermilab, Don was a rapporteur, and he described his analysis of 1,000 anti-neutrino and 1,000 neutrino interactions. And here you see the cross-sections very different, as would expect in the Quark-Parton model, and then he put some coefficients of the different things up here in this table. He then compared the integral of F2 for neutrinos with the value implied by electroproduction with some simple assumptions. And the neutrino data gave 0.49 plus or minus 0.07, and with some simple assumptions, the SLAC data suggested 0.52. So Don concluded that this agreement lends strong support to the view that the coefficients in table 6, that's the table above, in the energy range 1 to 10 represent the values in the scaling region at genuinely high energy. Oop, what have I done? I've turned it off. Here we go. Don then discussed quark model predictions, assuming spin a half, which he had shown was favored by the data, and here are some of the different predictions here. And then he turned to momentum. He showed that the Gargamelle data showed that the non-strange quarks carried about 50% of the energy of the proton, albeit with an error. He then put that together with the slack data and got a value for the momentum in the gluons of 0.46. But then finally he assumed SU3 symmetry for the quark-anti-quark C, probably not a good assumption, but with that he could get a much smaller error. Now, at the end of the conference, he discussed anti-neutrino data in more detail and looked at the Y distribution for different expectations of a value that he and Gerald called B, the integral of xf3 over f2. And here you see the anti-neutrino cross distribution. And on the right, in the proceedings, there's a sketch, obviously in Don's handwriting, showing with 3 quarks, the neutrino data you'd expect to be flat, and with just 3 quarks and glue, the anti-neutrino data 1 minus y all squared. I put that up because I'm coming back to it in a minute. The data are actually around 0.9 down there, so a very sharp fall off with anti-neutrinos. Finally, Don said, since the data described above come from experiments in the Gargamelle chamber funded by the French, it seems not inappropriate to quote a few lines from Voltaire. So I put them here for those who can read French, and for those who can't, I'll have refresh myself while you read what Don quoted from Voltaire. And then Don went on to say, this clearly warns us not to accept too literally simple pictures like the quark model, although in fact it was right. Now, the next event was the occasion when I really got to know Don well. It was the Hawaii Summer School, or Summer Topical Conference. There were 4 lecturers, each of us gave 5 lectures. And the 4 lecturers, Doug Morrison and Dick Feynman, had their families with them and they'd rented houses. But Don and I were on our own, and we were in the same hotel. We were having breakfast together every day, traveling to the school, spending time together at the weekends, or in the evenings when other things weren't going on. Well, you can see what we were doing on the weekends. This is us on the beach, the 4 lecturers, and in the middle, some of you may recognize Vince Peterson. Now, in Don's lectures, he first discussed neutral currents. And in the discussion of neutral currents, there was a very skeptical Dick Feynman, who at some point said, oh, so many neutral currents, why didn't you see them in the early experiments? And Don explained that Enoch Young had actually written the Monte Carlo program saying that well, first of all, he said, there's a neutron background which we can't exclude, it's all neutrons, but Enoch wrote a Monte Carlo program which showed that according to his program, the neutron background could only account for 1/3 of the events. So there probably were neutral currents. And at this moment, Enoch Young, who happened to be going through Hawaii and changing planes and decided to drop into the physics department, walked in at the back of the lecture theater, just as Don quoted him, and Don was left absolutely speechless. So by then there was some data from Fermilab, and you see down here at the bottom, the cross-section from Gargamelle, much smaller errors now than they had with the Freon and Proton data, now confirmed that slope right up to 100 GeV from Fermilab. Don showed the slack data, showing that things were spin a half, which the neutrino data also showed. He showed the Y distribution from Barish's experiment, and he showed the Y distribution from anti-neutrinos, and I'm stressing this for a reason you'll see in a minute, found in Gargamelle. He then showed that the data were consistent with non-integral quark charges. So there's the neutrino data in the black dots, and the anti-neutrino, the open circles. And that's the black curve is what you get with nothing but quarks. And you can see there's nothing but quarks. And the 18/9 thing worked at large x, but at small x there's a difference. And from that he figured out that there are some antiquarks in there, and you see that at the bottom. He looked at the F3 sum rule, and here there's two plots here actually. One is with the Bjorkane variable at the top, but at that time other people invented other variables which tended to the Bjorkane variable at infinite q squared, but were thought to show scaling earlier. And in fact, your paper uses the Bloom-Gilman variable, and this is the Bloom-Gilman variable at the bottom. And this is the data which, when this was all published, that was the data for that. Now I've almost finished, Roger. In the following years, increasingly accurate data accumulated from wide and barren anti-neutrino experiments at CERN and Fermilab. Apart from some hiccups, the data confirmed the underlying picture, and they showed scaling violations and QCD corrections to the sum rules. Now, what were these hiccups? They've sort of been forgotten, but not by me, and probably not by Dieter. So there was the alternating currents, which I'm sure you'll discuss. There was a so-called high Y anomaly. They claimed that the data doesn't go to zero like that at high Y with anti-neutrinos. There's a new phenomenon, and dimuons. And this generated a lot of excitement and many, many, many papers. And it came back to bite us in this country, because during the Kendra inquiry, a group of people in the Science Policy Unit at Sussex wrote a paper saying that CERN was grossly inferior to the American labs, and maybe we should leave CERN. And the evidence they cited for this was a number of papers published in the 1970s from Fermilab and CERN that attracted more than 100 citations in 1 year. In CERN in the 1970s, only one paper attracted more than 100 citations in a year. Anybody know what it was? It's the rising total cross-section. It wasn't the discovery of neutral currents. At Fermilab, there were 4, and 3 of them were these experiments here, I think. Now, unfortunately at that time, I didn't know, I wish I had known to tell Kendra, what happened after the New York Times article after the discovery of the Z. In July 1983, they ran an article with a headline, US not even Z0. CERN announced the discovery of the 2 W bosons, W plus and minus, in January, has now found the Z0. With that and the previous discovery of gluons at a German machine, European accelerators have established a better record of success than any of the 3 American labs. But unfortunately, we didn't know that. Now, Don left then Gargamelle. Gargamelle, by the way, was moved from the PS to the SPS, so much higher energy. And he was characteristically the first to analyze scaling violations and found that they were very similar in electron, muon, and neutrino cross-sections in a paper with Schreiner and Scott. And this was followed by papers that compared the moments of structure functions to QCD predictions. So here's a paper published in 1978 combining the old Gargamelle, I think the new Gargamelle too, data with the BEPS data, and you see the moments of the structure function. These are using a variable invented by certain Otto Nachman, falling off as the n goes up, because as you put up the power of x in the moment, you're probing lower and lower x, and we know the antineutrinos come in. Later I'm not sure where this was published, but it's in a historical article of Don's, he added CDS data and a scalar gluon line. I don't know what the scalar gluon line means, by the way, because you can't calculate with scalar gluons, not asymptotically free. But in 1983, Don was the co-author of 3 papers that gave the final Gargamelle and Baps results. Sigma L, or sigma S over sigma T, 0.08. The neutrino and anti-neutrino cross-sections, the coefficients of the linear rise given here, and then finally the F3 sum rule. So to conclude, while playing a leading role in particle physics, Don was also a good citizen. We've heard already that he was at a very early age on this emulsions panel. I interacted with him when he was head of department, the last head of department, because it became a sub-department after that with a different name. And I interacted with him when he was on the CERN Scientific Policy Committee. But in addition to that, he was the author of a superb textbook on which generations of particle physicists worldwide were brought up. He was a good friend, an inspiration, and a great physicist. And I will leave you with this here. Thank you very much.